or even when you are using some language, C or MATLAB or something, you will see that your answer will keep on coming in a particular format. In the sense, say for example, you will try to notice some representation, something like this, or but you will never see a representation, something like this. What is the difference between these two representations? These are just random examples. What is the difference between these two representation is you will have an exponent, a power function here, and you will have a power function here. It all depends on this integer portion only. Here, most computers will have this kind of representation and not this kind of representation. What is this? What is this kind of representation? That is, it has got more number of integer parts. Normally, whenever you are performing multiplication, you could see that you will have one integer part, and accordingly, this particular power will get adjusted. You will never see that you will get a random integer part, something like this, and then you will have some kind of powers. Okay, so that is what, and today what we are going to see is a floating point number representation in computers, right? So there are certain standards which are being followed by the computers, and we are going to see that particular standard only if we know how your computer actually represents your answers. You cannot think how to program, right? Because as computer engineers, you will be more interested in the program. If you want to do a better program, nowadays everybody programs, even a bachelor of computer application students, even class 8, some code junior, some kind of application has come. You can see in TV ads. Everybody has started programming. But how an engineer can program is entirely different from what even a class 8 student or a class 12 student program. The difference between a class 8 student or a class 12 student programming and an engineering student programming is whenever an engineering student programs, they will always think behind the hardware implementation, hardware implications. Okay, so how these particular numbers are calculated in terms of hardware? How is the electronics working behind in displaying these particular numbers? So that is the difference between an engineering programmers and the other programmers. Now let us slightly move ahead. So now normally uh, before the arithmetic operation, if you see, we were doing the complements, the first complements and second complement, the ones complement and twos complement for binary numbers. So here you can, I mean, we once in a particular place, we said that a complement of a complement is a original number. If you remember, so what is the complement of 1011 is? It is 0100. Again, what is the complement of this number is 1011, which is nothing but the same original number. Right. So this is just an extension of it, but represented in a purely in a mathematical form. If you consider your one's complement representation as a function of x, then if we want a function of this particular function to be x, then this function will be equal to x. So that is what is given here. What does it mean? It means that a one's complement of a number, you can get back that particular number again when you take the negative of that particular number. So that is what it means. Even this is true even for two's complement also. If you look the above theorem here, it's a simple mathematical relation here. If you have a negative number and if you want to get back the original positive number, you apply this particular theorem. So this is nothing but the recovery of a number. In simple terms, the complement of a complement is a original number, which we have already seen. So now let us move on to the floating point representation. First, I've already given you a glimpse of what is this floating point number representation is. But first, let us look at what you have studied. What you have studied so far is in the, especially in the number systems, you try to represent different number systems in binary bits. Say 13.25, you try to represent in terms of binary bits. You tried this fractional numbers, the decimal numbers in terms of different notations in hexadecimal, in octal, etc. Now, thinking from computer's point of view, if I want to store this particular number, and my computer, obviously you know that they handle only binary bits, and every computer bit has got a certain bit size architecture. So say for example, after you complete the digital electronics course, you will study a course called, you should have studied a course called as microprocessors. What is this microprocessors? This microprocessors is nothing but the child version of the existing computers. What is a child version? Once these digital electronics were in the making, Intel, they manufactured 4-bit processors. That is any arithmetic calculations, to be in a simple term, the old calculators. They tried to do a 4-bit processor which can perform addition, subtraction, division, multiplication, etc. You can store a data, you can retrieve a 4-bit data, etc. This 4-bit got multiplied, improved to 8-bit, then 16-bit, 32 bits, and now, sorry, 64-bit, and now you are having 128 bits encryption, in fact, 128-bit storage system. So we have improved a lot from 4-bit. So which means that if any number I am representing, say as an example here, 13.25, this 13.25 must be stored in this 4-bit only. So which means that this has got a limitation. So let us move on as per the theory that is written here. In binary, if the number of bits required to represent a number is fixed, then the accuracy of representing a floating point number is a problem. What does it mean? It means that if I am using 4-bit representation to represent 13. If I need to represent 13.75, then still I have to use these 4 bits only. Then I have to compromise in order to represent this 0.75 number. I have to compromise on the accuracy of the data, right? So that is a problem here, and representing the hardware limitation is a big problem in representing the decimal numbers, in fact the floating point numbers. Okay, so for example, as given here, to represent 15.53 theoretically, to our required accuracy, this integer 15, the maximum bit that is required is 4 bits. Whereas this 53 can be represented in a minimum of 7 bits. If you want this decimal fraction, it can keep on increasing, right? 53456420, etc. It can keep on increasing, and the size is also a limitation here, right? So, but in reality, what will happen? So how many bits is not just to represent 15.53, you need 4 bits to represent the integer and 7 bits here to represent 7 bits to represent the fractional part. So, but in reality, what will happen? But in reality, the processing bits, that is this particular bit size, they are of fixed size. If, say, for example, the processor is a 6-bit processor, you don't have 6-bit processor practically, but you had 4-bit, you had 8-bit, 16-bit, etc. But just for saying, if your processor is a 6-bit processor, then your accuracy of this particular fractional part is limited to only 2 bits. What does it mean? It means that if my processor is a 6-bit processor, 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. So which means this 4 bits, this 4 bits will be representing 15 corresponding to 1, 1, 1, 1. And the 2 bits, it has to represent 5, 3. But since we are having only 2 bits, what is the maximum bit that is possible? Maximum that is possible is 1, 1. So I cannot represent 5 obviously. I can represent only maximum of 3 value. So, but this value, so I can represent just only 1 and 1 here, meaning that the accuracy in fact here is reduced. So I'm not actually representing the actual value because of the hardware limitation. Instead of 5 3, I'm just representing 3, which is wrong. So, and how do we solve this particular problem? This is a hardware problem, completely a hardware problem. And how do we solve it? The above problem here, it can be solved by using floating point representations. Now, immediate question arises, what is a floating point representation? A floating point representation is nothing but computers, they have a certain format of representing the integers, the exponents, and the fractional part. That is what is called as the floating point representation. Let us see, there are multiple methods a computer has adopted over the years in representing floating point numbers. Let us see one by one. Finally, what is the method we currently follow is, we are following an IEEE format. There is an IEEE standard, especially for 128-bit and 64-bit processors. There is an IEEE format. So we are currently following those particular format. We will see that later. But before that, people, when they tried to solve this problem of uh, of addressing accurately the fractional numbers, the immediate simple method that came into their mind is this floating point emulation method. Let us see what is that. Now, floating point calculations, how do you know that it will have an integer part, right? Uh, so integer part as well as you will have a fractional part also, right? First, let us address the real problem and then let us move on slowly to the format. So nowadays, if you see, the computers, they are handling floating point calculations without any programming techniques required. Say when we were doing our BTech program, there were huge limitations of a computer hardware. So if our answer is, say for example, 1.5 into 10 power 129, you cannot see this particular number. Computer will display infinity, right? But the area that we were working required high accuracy. So big, why? Because our computer was limited to represent maximum number from 9.9 into 10 power 127 only. But our answer was 129. Still, this is not a very large number, but this is representing infinity, right? So there was a serious hardware limitations when we were doing our BTech program. But nowadays, if you see, computers, they can easily do the floating point calculations without any special programming techniques. So hardware themselves, they have been modified to take care of those shortcomings. So hardware themselves support nowadays floating point calculations rather than the softwares. Since, what is the difference here? If you are trying to handle these floating point problems using software, then there is always a serious problem in terms of programming techniques that one need to have, and at the same time, the uh, delay in computing the floating point results is always huge when you are applying a software knowledge. But if the same thing, if a hardware is able to perform this floating point calculations, it will be much faster. A simple example that I can tell you is, say for example, I have a switch, right? If you create a program to make the switch on and off, the executing of for this particular program will be larger when compared to a hardware switching. Say for example, I connect this to some electronic circuitry. I connect this to some electronic circuitry to make this on and off. This electronic circuitry, which is nothing but a hardware, will take much shorter time when compared to the software which controls on and off. So that is a simple example here. So let us take one example. Now any digit, okay, there can be n number of decimal places you can represent. So for example, what is 0.5 into 0.25? Though it is 0.125, I can keep on putting any number of zeros here. But scientifically, how these are represented is the 0.125 computer, even if you have a calculator, you just verify now. Okay, you multiply these two numbers and see, and there will be one mode called as engineering mode, IENG mode, right? If you have calculator in hand immediately, just look at what is this particular function of this engineering mode. This 0.25 is often represented as this particular format only. What is this format? This has got an integer value. this has got a decimal value. This has got some 10 powers. I mean, 10 is multiplied by 10 is a default value, and this minus 1 is nothing but the power, or the exponent power. Okay, so you could relate this to already, we have already seen, see, this is minus 1. You should relate immediately whenever you are getting minus here, then immediately what must come to your mind is how is this minus represented in hardware, right? So we have already, just as we have in the last class, we studied the signed binary number system. So that you must recall. Similarly, this is a small number representation. A large number representation, something like 5 lakh. This is also represented in the same format. Look at the format here. The formats are same. You have an integer part. You have a fractional part. You have this 10 multiplied by 10 is a default value, or even if you don't write, that is taken as it is. And you have the exponent part here as minus 1, and you have exponent part here as plus 6. So comparing computers, they always use these kind of notations either to represent a small number or even to represent a larger number. What is the advantage of this is, the advantage of this is this 6 here, anyway this is going to represented, this is going to be represented in a certain bit format only. Say, so which means that if it is an 8-bit representation, then you are going to represent it in a larger range. The range of these number representation largely depends on this particular size. Just a minute, I'm getting some call. Okay, sorry. All right. So such a representation. Now let us bisect this representation. So this kind of representation, now it will have 3 components. What are those 3 components? Number 1 is a sign bit representation, right? Now, this is very important. And then the mantissa part, the exponent part. The computers, they will have a fixed format. If I say, for example, I'm having a computer with an 8-bit processor. If it is an 8-bit processor, I will have 8 different bit sections, 1, 2, 3, 4, 5, 6, 7, and 8. This 8 bits are the one that is you going to be a standard field. We call it as a fixed field, where the first field will be representing the sign of that particular number. Okay, and there is and rest all will be different values. So likewise, there is a rule here. So here computers, in order to represent these kind of formats, they have a fixed fields. So this is how their field will look like. This is how their field will look like. They will have a sign bit here. The first bit will always be a sign bit. And then you will have an exponent bit. What is this exponent bit? This exponent bit is nothing but this minus 1 here, right? This minus 1 will be represented somewhere here. Say minus represents 1 here, and then 0, 0, 0, 0, 1, depending on the size of this particular um, bit format. Similarly, the significant. What is the significant? This 1.25, out of this 1.25, we need not represent this 1. And only 25 is represented as a significant here. This significant will tell you how much precision of representation you want. So you want to represent 25 or you want to represent 2501. It all depends on this particular significant value. And at the same time, this particular field, the exponent field that is written here, this will give you the range of this particular exponent. If it is a 4-bit exponent, then I can go from 10 power minus 5 to 10 power plus 5. If it is a 8-bit representation, then obviously I can go from 10 power, this particular value, this will be 2 power 8 now. Okay, so likewise, now let us take some examples. Now let us first take a simple model. What I mean by simple model is I am going to take certain bit sizes of this particular fields. let me take an example, then maybe you will clear. Now in this example here, I'm going to take a floating point representation of 14 bits in length. What do you mean by 14 bits in length? It means that I will have 14 different fields. So I'm going to write here, the first bit is going to be the sign bit here, and then 14 fields. I'm going to divide that my exponent will be represented as 5 bits and significant fields will be represented as 8 bits. So my exponent field 1, 2, 3, 4 and 5, right? So these are my exponent fields. Then I will have these significant fields 1, 2, 3, 4, 5, 6, somebody count 1, 2, 3, 4, 5, 6, 7, 8. Okay, one next. All right. So this is an 8-bit field. This is an 8-bit field. This is a 5-bit field. And to represent a sign bit, it is 1 bit. So this is your exponent field and this is your significant field. This is a simple model of 14-bit representation of numbers, floating point numbers. Now what is my rules? I'm going to set some rules to fill this particular 14 bits of data. What is the rule? Always, the significant is always preceded by an implied binary point. What do I mean by that is, in this particular example, you see here, I'm going to represent 5.52 into 10 cube. In this 5.52, I will not represent as 5.52. I will always represent any number as 0.552 and I will adjust this 10 power 3 based on the movement of this decimal value. I moved it to my left, right? If I moved it to my left, I add 1 here. So it is 10 power 4. Always it is preceded by an implied binary point. The data that I want to represent 552 is always preceded by my decimal point. Always I will have 0 in front of it. So which means by standard, I'm not going to represent 0 at all. All I'm going to represent is only this 552. Another example maybe I will take here. Another example to take is, say for example, I want to represent 25.32 into 10 power 5, just for example. First, this is a human interpretation of a number. But computer, if I'm using this kind of a format and I'm setting these rules, first I will convert this number into a number that always have an integer part as 0 and a decimal point, and all these numbers will be represented after a binary point only. So if I move this 2 places now, and I'm going to add to the power 2. So now my computer will easily understand that I'm having 0 point in front. And if I'm representing, I will be representing 2532 in the significant in this particular region, and the 7 will be represented in the exponent value. So the computer will understand that it is 0 point, and at the same time it is multiplied by 10 to the power something. Okay, so these are certain rules that I'm going to check. The first rule is it will always be preceded by an implied binary point. Second is the significant always contains a fractional binary value. So this is the significant part. The 552 is the significant part. It will always contain the fractional binary value. Okay, and the third rule is the exponent here, that will be always be a power of 2, meaning here there is a slight mistake here. If I want to represent 10, so if I want to represent 10, then the value that here it is possible is 2 power 3, which is closer. What is closer to 10 as a power of 2? 8 is closer to a power of 2. So I have written approximately equal to 2 power 3. Similarly, if I want to represent 1000, then what is the number closer to 1000, which is a power of 2? 2 power 10, which is 1024, is closest to 1000. So I will be representing as a power of 2 only. right? So these are the three rules that I have framed to use this 14-point number. Use this 14-bit format. Now let us take a real example. So the question here is, I need to represent this 30 decimal number 32 in a 14-bit floating point model. First, it is a 14-bit floating point model. When I represent this 14-bit floating point, first thing that I need to make is I must create these fields of 14-bit. So I have created a field of 14-bit here. So this is a 14-bit field. If you want, you count it, okay? So I am not spending time here. So maybe I'll count once, then you assume it. 1, 2, 3, 4, 5, and 6. 8, 9, 10, 11, 12, 13, 14, 15. So, okay, there is a 1 0 extra then. 8, 9, 10, 11, 12, 13. Yeah, 1 0 extra. Okay. Now, okay. So according to my first rule, what is my first rule? I will first convert this 32 into this format. 1 into what is 32 equivalent to in terms of the one that is closer to 2 power, it is 2 power 5 is 32. So this is in terms of scientific notation. Now immediately I will convert this 32 into the scientific floating point number representation, which is nothing but 1 into 2 power 5. So 1 can be 1.0 is not a standard format. I must always have 0 point something, 0 point something. So I have converted this 1.0 to 0.1 and I have adjusted the exponent value here to 2.6, 2 power 6. So according to the point 3 now, let us look how your field gets filled. So this is a positive number, right? This is plus 32. So my sign bit here, is 0. Now this is an exponent field. How do I represent 6 here? It is represented as 0, 0, 1, 1, 0. Okay. So that is how it is 6. And then what is the significant field I have? I have 1. So my first bit is 1 here and then rest all it is 0. This is one way of representing. There is additional way of representing here. I'll just show you how. This is the standard way we just saw. 0.1 into 10 power 6. If you want, you can represent it as 0.01 into 10 power 7 also. In that particular case, how does the format will change? This is the exponent part. So exponent part, instead of 6 here, you will get 7, 1, 1, 1, 0, 1, 1, 1. And then the significant part is 0, 1. So it is 0, 1 is represented here and rest all 0. Similarly, there are more formats. If you want, you can represent the same number as 0.001 into 10 power 8. So exponent part 8 is represented as 1100 and the significant part is represented as 001 here, so 001. And one more example finally, 0. So same example, you can add more zeros here and the exponent get increased by 1. So 9 can be represented as 1001 and then the significant part can be represented as 001, etc. Now there is a serious disadvantage here. What is this particular disadvantage here is this definitely it is not an effective way of utilizing the space. What is the effective way then? And one more important thing is how do you represent negative numbers? Obviously, the negative numbers here, if this number is minus 32, then I can just put 1 here because representing, so this is a sign bit representing minus 1. What if I have a number 0.1 minus 0.1 multiplied by 10 power minus 6? Then I cannot represent in this particular format. In the beginning itself, I said that I'm just going to test. I'm creating my own rules. So this is a very simple model, an example model only. This is not a standard model. So in order to overcome this particular problem, what is this problem? That is, if I want to represent a power of negative number, it is not possible. And at the same time, there are huge wastage of spaces here, right? So, and this will create confusion also, right? See how many spaces are wasted here. All these bits are wastage of space, right? So in order to avoid this, what we can do is we are trying to create a slightly a standard format of representing floating point numbers. So as I mentioned here, we cannot express zero point 0.5. What is 0.5 close to, what is the one number which is close to 0.5 in 2 powers? It is 2 power minus 1. So which means that this exponents field is a negative value, and we don't have any sign bit representation for exponent field. We have a sign bit representation for the complete number. This one. This one, all these numbers, they are for the whole number, but not for the exponent number. So the above two problems can be fixed without much changes to this particular model. All we need to do is just we have to change the rules. Now, what is the rule I am going to change is, previously I created a rule such that my number will always be represented as 0 point something. I created a rule such that the number will be 0 point something. Instead, I create a rule such that the number will always be represented as 1 point something. Let us see how it makes a difference. Now, the first digit of the significant must be 1. Okay, with no ones to the left of the radix point. Let us see how to implement that. I said in the previous standard format it is 0 point something, but here it is not 1 dot, I'm sorry. Now here I'm going to create a rule such that I will always have 0 0.1 and then the value. Let us see whether it is possible to implement or not. This method of representing a 1 after a decimal point and no ones before that, this is called as the normalization procedure, normalization format. Now let us see an example, then maybe you will appreciate. All the significance must have this particular format. What is the significant? Let me recall. These are the significance. These are the significance. All these must have a format. Here it is 0 0.1, right? This is a okay format. 0 0.01, no. Why? Because I must always have a 1 after the decimal value. Whether it is possible to implement, let us see now. So all significance must have the form 0.1 and any value. Say we want to represent 4.5. How do we represent 4? Normally, 4 is represented as 100. 5 is represented as 101. So the equivalent decimal value here, 4.5, is 100.101. This is the way of representation. Now, please note here that we are having 1 after a decimal value, dot 1. So we are having 100.1 multiplied by, and we don't need any powers, right? But still you need to represent the exponent value also. So what is the exponent value? It is 2 power. We don't have exponent value, so it is 2 power 0, right? And the same number, as per the mentioned rule, please note here, we must have 0 point, right? So your integer part must always be 0 here. And how do you make this integer part 0? Move all these 3 bits into the decimal value. So this can be represented as moving the decimal value towards your left. You add the number of bits that you have moved, number of positions you have moved to your left, add a positive number to the exponent value. So it is 100.1 can be represented as 0.1001 into 10 2 cube. Right. So now what will happen? The first disadvantage. What is the first disadvantage? That is, we are using all possible spaces here. Right. The first disadvantage is solved by the above rule, which means that previously we just had 0 point something. So if we had we had so many number of spaces getting wasted here, right? Now these spaces now it gets filled by significant values equal. So here the significant values, what are the significant bits here? 1001. It gets filled in these particular spaces. It gets filled as 1001 and 000. Though you may argue that these are wastage of spaces, but this is just a simple example that we have given. When you handle large numbers, then you will see that all these bits will be filled with some significant values. Now let us see, let us go back to our rules here. And the second disadvantage is solved by putting your negative exponents. Now the immediate question comes, how do I give a negative exponents? Now, in order to avoid the negative exponents, what we are going to use is, we are going to use a concept called as biased exponent. In order to represent the negative exponent here, we are going to use an exponent called as biased exponent. What is this biased exponent? Say for example, I want to represent -2. Okay, then I make this -2 as a positive number by adding some standard value, say for example 50. So -2 plus 50, 48. So my computer will understand that 48 corresponds to -2. How does it understand? It will subtract by default the given number with 50 such that you get the original number. Okay, so similarly, what we are going to do here is, I just gave you a random number of 50. Likewise, you must see what is the range of values that you want to represent. Meaning, say I want to have exponent values ranging from -127 to +127. I want to represent values ranging from 2 power -127 to 2 power +127. Then what I do here is, according to me, -127 corresponds to 0 and +127 corresponds to, I add 127 to it. So how much it will be? 4, 5, 254 corresponds to +127. Whenever I want to find out what is the actual value, I will subtract 127 from it. So as with this in mind, what I'm going to do is, I'm just going to give you a very simple question here. How much is 100 and say 100 represented? What is 100 equivalent to by this biased exponent value? So if 100 is given in the exponent value, all you need to do is subtract 127 from it. So -27 corresponds to 100. What is 200 corresponding to? 200 corresponds to 200 minus 127, whatever it's the value. So it is 73 is the value which corresponds to 200. I hope you understand this. Any doubt here? Anyway, we are going to see in detail. Any doubt so far? Okay.
Excuse me, sir.
Yeah, please go ahead.
Earlier we were considering the powers of 10. Now we are considering the powers of 2.
Okay, this example, yeah, could you mute? There is noise.
Sure.
Yeah, okay. Very valid question. Okay, why did we do this here is, we are handling decimal numbers here. Please note 32. We never converted it into a binary value. 32 to the base 10, which means that a floating point number we are trying to represent the decimal number we are trying to represent in a 14-bit floating point number. So that is the reason here. Otherwise, it is actually 2 powers only. So all these are decimal way of representing the floating point numbers. And unfortunately, what has happened here is 32. Oh, did we represent? Oh, we have converted into binary here. Yes, you are right. So there is a mistake. Because here in this example, if you see, it is into 10 power, meaning that these are decimal values. That is why it is 10 power. if we have converted this 32 into binary value, yeah, then it should be 2 power, sorry. Then it is by mistake. All these are into 2 power. Yeah. Okay.
Okay, thank you, sir.
Yeah, yeah. Good. Thank you for pointing out the error. Okay. All right. So now let us move on to the thing that I was telling about the biased component. So now what is a bias? Bias is a number that is approximately in the midway of the range of values expressible by the exponent. Now, how did I get this 127? You might think, how did I get this 127? 127, it is in fact 2 power 0 to 127. 0 to 127 corresponds to total 128 values, right? So it is 2 power how much? 2 power 4, 2 power 6, I think 2 power 7, I believe. 2, 2, 2, 2 to the 4, 4 to the 8, 8 to the 16, 32, 64, and 128. 1, 2, 3, 4, 5, 6, 7. Yeah, 2 power 7 corresponds to 128. Okay, so here bias is a number that we will always choose, which is in the midway of the range. If you want to, if we have an 8-bit processor, 2 power 8, then total values that we can represent is 256 values. So what is the midway of 256? Midway of 256 is 128 and 0 included. So the range will be from 0 to 127. Okay, so midway will be 127. So that is how we need to take. So what we do here, once we choose the midway of the bias value, we subtract the bias value from the value of the exponent to determine the true value. So just again, though we have discussed multiple times, I'm just giving you a simple example here with 5-bit exponent. If I have a 5-bit exponent, what is the range that I can express? Minimum 5-bit can be represented as 00000. What is the decimal equivalent? 0 to the base 10. What is the maximum value 5-bit representation? It is 1111 and the decimal equivalent is 32 to the base 10. So which means we can represent total 32 values, but what is, if you want to represent negative values also, then we will represent from minus 16 to plus 16. Instead of 0 to 32, only positive value representation. If you want to represent a negative value, then we will represent from minus 16 to plus 16. So the bias in the above example here, in this particular example, what is half of 32? 32. Half of 32, that is the maximum value is 16. So the bias here is going to be 16. Only then, if I want to represent minus 16 here, I add plus 16 to get 0. If I'm giving us a 0 value, it means that the actual value equivalent is minus 16. Okay, so this is called as excess 16-bit representation. You might wonder what is this new format. We are going to see all these things later. This kind of format is called as excess 16 representation. Here in excess 16 representation, the bias value less than 16 are negative numbers and bias value more than 16 are positive numbers. Okay, so quickly, maybe 5 more minutes, we will do one example and then we will move on tomorrow on Friday with some improvement in this particular model. Okay, again, I have taken 32 as an example. Previously, if you recall, we took this 32 to the base 10 in a just an example model, my own model, right? So we took this example as 32, right? We represented as a standard 14-bit model where 32 was converted into 2 power 5 in scientific notation, and we did all these examples. Now, okay, now 32 again, it can be represented as 1.0 into 2 power 5. We always wanted 0.1 and then the rest of the values. So this can be represented as 0.1 into 2 power 6. Please note in the biased model, revised means inclusive of bias. Inclusive of bias. So 6 will not be represented as 6 actually. What should I do? I should always add 16 to it. So I will add 16, meaning 16 plus 6 is going to be 22. So in decimals, in binary, 22 was given as 10110. Now, how will be my floating point model? First, this is a positive number. This is plus 32. Hence, the sign bit is 0 here, representing that it is a positive number. What is the exponent equivalent to 10110 after biasing? It is 10110. Now, what will be the range of this particular biasing? If it is a 5-bit, it will be from 0 to 31. Okay, so total 32 values, 32 powers of values. Now, what is the significant value? Significant value is 0.10. So it is 1000, etc. 1000, etc. This is your significant value. Now, if you want to get the original exponent, then if you as a human, if you want to interpret what is this particular value, this is a Hoek's value, this is a virtual value, like virtual classes. This is a virtual value. So if you want to encrypt what is the actual value of this exponent, all you need to do is subtract this value from 16, right? So 10110 is 22, you know, subtract 16 from it, you will get 6, right? So that's what it means. Okay, and in order to get you familiarized with more coax exponential values, I have taken few more examples. What if the exponent entry here is 01000? Then what you should do? The equivalent 01000 value is 8. And to get the original value, all you need 8 minus 16. What is this? It is minus 8. So 01000 corresponds to minus 8. Okay. All right. So I think we will stop here. We will continue after this in the next class. Any doubts so far? Your problem set 2 is based on these floating point numbers, so try to listen carefully. Any doubts? Okay, so thank you. If there are no doubts, then you may exit the meeting. Thank you, Sanskar. Thank you. Yeah, everybody. Thank you, Akriti. Thank you. Sanskar, did you ask your friends they want to submit the tutorials? I don't think so. Sanskar? Oh, Sanskar has left. Okay. It doesn't matter.